In this particular question, we've been told that we have a lot which is comprised of two equal rectangular playing fields having one side in common. That is, the playing fields have one side in common. The lot is enclosed and divided by 600 meters of fencing. We have to find the dimensions of the lot such that we obtain the largest possible area for the lot. Well, we first start by drawing a diagram, and we're going to label the sides of our rectangle, and I'm assuming it's a rectangle at this point in time. I'm going to say that my width is x and my length is y. So you'll note by my diagram that I actually have 3 x's and 2 y's. Well, they told us that 600 meters of fencing encloses and divides the lot. So we can now say that 3x plus 2y is equal to 600. We've also been told that we want to find the dimensions such that the area of the lot is maximized. So we'll be using the formula for area. In the case of a rectangle, area is equal to length times width, or x times y in our case. Now, when you look at that equation, you'll note that it has 3 variables, a, x, and y. This isn't a function. We tend to understand how to find minima and maxima for functions. So what we'd like to do is somehow express one of these variables with respect to another one of the variables, such that we go from 3 variables down to 2 variables and then have a function. Well, we return to our first equation, 3x plus 2y equals 600, and we rearrange that equation such that we can solve for y in terms of x. And we end up with y is equal to 300 minus 3 divided by 2x. So I can now substitute this in to our area equation. I can now substitute this expression, 300 minus 3 over 2x, in for y. So I end up with a is equal to x times 300 minus 3 over 2x. I expand that using my distributive property, and I end up with a is equal to 300x minus 3 over 2 times x squared. Now what I'd like to do is take the derivative of that. So a prime is going to be equal to 300 minus 3x. We know that the slope of a tangent line at a maximum or minima is equal to 0. It could also not exist in some cases. But we'll set this one equal to 0 and solve for x, and we end up with x equaling 100. Now we have to find the corresponding y value, the other dimension. Well, I know that y is equal to 300 minus 3 divided by 2 times x, so I merely substitute in 100 for x. And I solve for y, and I get 150. Now, the only thing I have to check on is this indeed the values that maximize my area? So I take my second derivative, a double prime, which happens just to be equal to negative 3. So it doesn't matter what value of x I choose, my second derivative, a double prime, is always less than 0 because it's always equal to negative 3. So because that second derivative is a negative, we know that we are indeed dealing with a maximum. So we can conclude that the dimensions of the lot are 100 meters by 150 meters. Now we're going to look at an alternate technique for solving this same question, where we've been told that we have a lot which is comprised of two equal rectangular playing fields having one side in common, and that the lot is enclosed and divided by 600 meters of fencing. We want to find the dimensions of the lot such that the area is maximized. So we start the same way as we did before. We draw our diagram and label our sides, x and y. And then we write down our two equations. We know that 3x plus 2y is equal to 600, and that the area is going to be equal to the length times width, which in this case is our x times y. Now what we're going to do is differentiate both of these equations with respect to x, because both of the equations have the variable x in them. I could have just as easily differentiated both sides of this equation with respect to y, because both of these equations have the variable y in them. So when we do the implicit differentiation on the first equation, we end up with 3 plus 2 times dy dx, which is equal to 0. When I differentiate the second equation with respect to x, or use implicit differentiation, I end up with dA dx is equal to x times dy dx plus y times 1. I've had to use the product rule here. So I return to the first equation that I was working with, or to the left-hand side of the screen. And what I'm going to do is rearrange and solve for dy dx. First, what I'm going to do is subtract 3 from both sides of the equation. So I have 2 times dy dx is equal to negative 3. And then I'll divide both sides of the equation by 2. So I end up with dy dx is equal to negative 3 divided by 2. Now I return to the right-hand side of the screen. I know that at a minima or maxima, the slope of the tangent line is equal to 0. So I set dA dx equal to 0. That's going to be equal to x times dy dx. Well, we just found out that dy dx was equal to negative 3 divided by 2. So I substitute that in, and I add to that y times 1, which is merely y. Now what you'll notice with that equation is that I have two variables, x and y. It'd be nice if I was only working with one variable so I could solve for that one variable. So I return to my original equation on the left-hand side of the screen, which was 3x plus 2y equals 600, and I take that equation and I rearrange it such that I express y in terms of x. And what I find is that I end up with y equaling 300 minus 3 divided by 2 times x. So I now can substitute this in for y, and that's what I do on the right-hand side of the screen. So I end up with 0 is equal to negative 3 divided by 2 times x plus 300 minus 3 divided by 2 times x. I now have an equation with one variable, x, in it. I now should be able to rearrange and solve for x. So I subtract 300 from both sides of the equation, and I end up with negative 300 equals negative 3x. The negative 3x is the sum of negative 3 divided by 2x and negative 3 divided by 2 times x. With that equation, I can now solve for x. X is equal to 100. And then I take that value of x, substitute it into the equation y is equal to 300 minus 3 divided by 2 times x. And I can solve for the corresponding y, and I end up with y equaling 150. So I just put in the units of measure. It's 100 meters and 150 meters. These are the same answers that we obtained when we used the first method.